Any questions about anything before we get back into this section? Okay, so we did a few different approximation methods. The one that we have yet to talk about is this one called Simpson's rule. So if you're interested, there's a much longer derivation and rationale for this, for how this thing came to be. I'm not going to spend a ton of time talking about it right now, but basically the short rationale is that this mathematician Simpson devised this rule to basically assume that whatever curve you're trying to find the area underneath takes the form of a polynomial, and from that he devised this formula. So basically the big sequence to pay attention to is this. So your delta x stands for what it always has stood for. Basically, however wide each one of your equally wide subintervals are. And then the sum on the inside, you'll notice the coefficients basically go 1, 4, 2, 4, 2, 4, 2, and so on. So basically the sequence begins with 1, the coefficients are 1, 4, and the last two are 4, 1. And then in between, it alternates between 2 and 4 and 2 and 4, and so on. I will give this to you. I do not expect this to be a thing that you memorize. So I hate to be so kind of vague about where it came from, but do we understand it well enough so we can at least use it once? Okay. So same integral we've been approximating. This time I'm going to alter delta x a little bit. I'm going to say that we're going to use 5 subintervals. So if we use 5 subintervals, then what's the delta x that goes along with that? How wide is each one of our 5 subintervals going to be? 0.4, right? So full width of the interval divided by 5 comes out to 0.4. So based on that, I need to find value of this interval is spaced that evenly. So 0.4, 0.8, 1.2, 1.6, and then 2. All right. Can we get y values for each of those x values? So the endpoints are a little easier to do, so I'll do those. If someone can calculate some of the others, that'd be great. Which one? 0.69? Okay. 0.89? Okay.
1.6 is 0.9. 1.2 is 0.99. 4.98. I was doing this 0.9.
Okay. That looks better now. All right, so if I want to apply Simpson's rule to approximate this area, the integral from 0 to 2 of our function is equal to 1/3 times our delta x. Maybe I should just put these things in general terms for now. Times f of 0 plus 4 times f of 4, or f of 0.4. Plus 2 times f of 0.8. So we have an even number of points that we got. So remember, we know the way this ends is with the coefficients of 1 and 4, and we know it ends with the coefficients 4 and 1. And like I said, we alternate kind of in the interior, 2, 4, 2, 4, and so on. But since we have an even number of terms, we are going to basically have to double up on the twos. Any questions? Go ahead.
How do you know what numbers you put the 4 in and what numbers you put the 2 in?
So the 4 will always go. So the first one is always going to be the second term in the sequence. And then the last one will always be the second to last term in the sequence. So this
How do you know like what numbers to use?
for the coefficients.
Yeah.
It's also it's always either 1 or 2 or 4. So the bookends, the first and the last terms are the only ones that are just coefficients of 1. Everything else will be 2 or 4.
Okay.
So then it's essentially you alternate. But you have to alternate knowing that basically the second to last one is going to have to be 4. So basically that's why the twos are doubling up there. So maybe another way to think about it is think about it, instead of like going from left to strictly from left to right, like from first term to last term, think about you like coming in from from both sides.
Yeah.
Both sides are 1 or both. So the first and last term both have coefficients of 1, right? Then the next 2 terms in have coefficients of 4. And then the next 2 have 2. And then you keep going until you basically run out of terms. So we have an even number of terms. So we have 3 pairs, 1 on the outsides, then 4 going inward, then 2 in the middle, right? If we have an odd number of terms, you have that 1, 4, like coefficient of 4 for the very middle term. But we don't have an odd number of terms, so we didn't see that happen.
Okay.
Anything else about this admittedly very arbitrary seeming formula? Okay, so can we start plugging in some of our values? So 1/3 times 0.4. I'll start writing out the way the calculation is set up. If y'all want to start marching towards a final result here, that'd be awesome. And I think the remainder or most of our answers have kind of been around like 1.6, something between 1.5 and 2. So this better be something close to that. I got 1.18. I would trust your real calculators more than mine.
Yeah, 1.47.
Awesome. Do we have agreement between any 2
It
people?
looks like the last one you did 1.6.
Yeah. Set up for it.
Oh yeah, that doesn't make any sense. Okay, so don't trust mine because I definitely followed this. I also thought mine came out too low. Good catch there. You got 1.47? Okay, so I heard 1.47 from multiple people, so. And it seems reasonable. This is the wrong sign to use here. Approximately. So 1.47 seems reasonable. It seems it's in line with some of the other things we found with our other approximation schemes. Any questions about how we applied this? Go ahead.
Is it always gonna be 4, 2, 2, 4? Or is it ever gonna be like 4, 2?
So let's we're not gonna go through it again, but let's do this. Let's go back to the way that we've done it before. So we did 5 subintervals, and so we did 5 subintervals and followed up from there. What would happen if we did, for every other thing we did 4 subintervals, right? So if we did n equals 4, that's going to give a delta x of 0.5. If we do that, so if we look at 4 subintervals, we're looking at 5 boundary points, right? So if we look at those 5 boundary points, then what's our sum going to be? It's going to be 1/3 0.5 times. So the first and last terms are always just the unity. So 1 times them. So f of 0 and f of 2. So that is the same as the way we dealt with this. What are the next 2 terms inward going to be? It should be 4 times f of 0.5. And 4 times f of 1.5. Okay, so if we handle in pairs, this might be easier to see the way the coefficients drop in. So now, what are the next 2 terms going to be? Those are going to have coefficients of 2, right? But how many more terms are left?
1.
Just the 1, right? So in this situation, I just have the 1 coefficient of 2 right in the middle. Because in this case, I do have a middle term. Because I have an odd number. Did that answer your question? Okay. Anything else? Okay. All right, now we get the exact value. So can we find this integral without using any of our approximation tactics? Can we get this exactly?
Yeah.
How do we do integrals like this?
U
substitution? What's a good value for you? Yeah, I got to vote for 1 plus x squared. If I do that, then what else do I have to deal with? du, which is 2x dx. Does that help me with this integral? The integral from 0 to 2 of dx over, no, du over u, right? Are we done? I see one subtle but very important thing we still have to clear up.
Balance.
The bounds, right? So these 0 and 2 are actually, even though they're not explicitly given to you like that, those are x values. So we still have to redefine those. So yeah, the integrand is going to be du over u. What are the bounds going to be?
1, 5.
1 and 5? How'd you get 1 and 5?
You plugged in the previous bounds. You in terms of x.
So we made, basically we have a formula that translates x to u that helped us transform the integrands into u form, but now we can also use that to get new bounds. So now we're integrating du over u from the bounds of 1 to 5. What is the integral of du over u? What's that? Very close.
Absolute value.
absolute value. It's not going to matter here because I'm not taking any negative values for you, but still. So this comes out to be the natural log of 5 minus the natural log of 1, right? This goes to 0. So our final integral is natural log of 5, right? And since we've been approximating everything, let's get a decimal that value from natural log of 5. I got 1.609. Okay, so not terribly far from some of the things we got before, right? How are we doing? Okay, go ahead. Yep.
Why did you do this ln5 minus ln1? We don't have to plug in u again?
So those, the 1 and 5 there are the bounds for our integral.
Oh, we already did that?
Yeah.
Oh,
Yeah, so the 0 and 2 are our bounds for x. But then basically we traded that integral for an integral involving the variable,
oh.
which is why the bounds changed as well. Go ahead.
Wait, why is this approximate integration?
This one's not.
Oh,
No, so basically everything we did up to this, that all was to approximate this integral. So the ones you'll see in the homework, if you haven't already opened it up, many of those are antiderivatives that you don't know how to find.
wait,
So-
this is just a check that.
Yeah. Oh, yeah, so this one, yeah, admittedly, all the approximation stuff didn't really need to do it with this exact function, but I wanted to lead up to something we could like really find the exact numbers of. But yeah, for the homework, I think probably all the ones I gave you are things you have to approximate because the antiderivatives are not available. How are we feeling? Okay. I got one more thing here. I think I'm gonna leave that one. Actually, let's talk about it a little bit. Let's not do the whole thing, but let's talk about how this is done. So basically this graph shows us a rate of change. So on the x-axis, we have time scale. So divided up into increments of 3 hours for an entire day. And on the vertical axis, I have basically the amount of data that's being either downloaded or uploaded on a network in megabits per second. So if I were to find the area under that curve, what would that give me? Go ahead. Total number of megabits. So yeah, so basically the total amount of information that's been transferred on that network. Actually, I'd also have to adjust the scales because one of them is in hours, the other one's in seconds, right? So there'd have to be some kind of conversion there, but that's essentially what that area gives you. And this one thing we've talked about with integration, the quintessential way to think about integrals is it finds the area underneath the curve if you look at the graph, right? Another really important way to think about it is that if you look at the function that you're integrating as being the rate of change of something, then integrating that function gives you the total amount of change that there was. So in this case, the total amount of information that has been transferred on this network. So how could we approximate the area under this curve? What's that?
Dividing the shapes.
Divided into shapes, right? What shapes do you want to use? The rectangles are that's the most basic one we talked about, right? Let's just kind of go with the scale. So I'll make these rectangles each 3 hours long. It's a weird thing to say, but in terms of their width, they're going to each have a width of 3 hours. And if we're going to use rectangles, what else do we have to decide? Endpoints. What do you want to do? Left? Left sounds good. So I'm gonna get an overestimate there, right? Overestimate there. Gross underestimate here. These ones up here will be more or less faithful. So once you, like, let's say we use left endpoints to divide up all those areas, could you find the area of each one of those rectangles? Right. So there is at least one question in the homework where you're asked to use this approximate integral without being given some algebraic definition of this function. Like, I don't have any idea what the mathematical expression for that function is. But if you can get your hands on the graph, you can still kind of apply all those approximation schemes. How would you go ahead?
We still use distances.
Yeah, so I chose rectangles because that was the first thing I heard. So any of the things that we talked about in this section could be used here. They're all going to give you slightly different numbers, obviously, just like the way we saw, or maybe not so slightly different. I think in this one, if I use left endpoints, I've been looking at that one interval in particular from 6 to 9 hours. Left or right endpoints are going to make a monumental difference just on that interval. So they'll all be different. Sometimes those differences will be really significant. There's also nothing saying that I have to divide it up into 8 chunks like I was about to. You could do every hour or every half hour if you have the time and the interest. So I think we're going to stop there if that's okay. Okay, that is all I have for you for 6-5, and that's all I have for you. That's going to be on the first test, which is when? Next Monday. So one thing I want to show you that I put on Canvas pretty late, so I don't know if anyone saw it. So I downloaded a bunch of quizzes from from somebody else's class in here. I tried to hide them all from you except the one I wanted you to see, but if you see them, don't freak out. I'm not assigning them. It's just this. So module 5, which is this week. So in addition to the headings I always have, there's one here that says exam review. So this practice exam right here, basically it's structured like a Canvas quiz, but it's not being graded. But basically there are, I think, 29 questions in here. So some free response, some multiple choice, of things that are, that are like of appropriate content for what are going to be on the test on Monday. So I'm not grading this. I'm not mandating that anyone do it. I think it'd be a very good idea for y'all to look at it, but I wanted y'all to be aware of where it was. Question?
Are we gonna know, like, at the end when we submit it, what was the right answer?
You'll get instant feedback on it. Not for the pre-response ones, but based on something I showed you last time, you can go to Wolfram or Symbol Lab or whatever, and you can get that integral right away. Hopefully, after you try to do it, to make sure you are on the right track. But for all the multiple choice ones, I don't think it'll give you instant feedback. I think you'll have to submit the whole thing to get that kind of feedback.
Okay.
But I think, yeah, like these integrals, you'll be able to. That's kind. For these integrals, you'll be able to put those in like Symbol Lab or something. Also, I think I put some links in here of some other ones that I know work. Yeah, online integral calculators. There's one that gives you a step-by-step process. So if you use that one, at least tell me about it. I think the whole point of that is to make it look like you're showing your work, even if you're just writing them all down for somewhere else. Okay, so also there's a website that has a bunch of old tests from previous Math 266 sections. So there's a bunch of review stuff there. Also, I took a screenshot of the part of the syllabus that identifies problems in the textbooks you can do that are in those sections. So lots and lots of stuff you can start reviewing on. I recommend strongly starting now as opposed to the weekend. That way, if you run into trouble or if there's just something you need to brush up on, trying to get a hold of me during the weekend is a lot less reliable than during the week. So if you can start reviewing now, that'd be better. Go ahead.
So there's a quiz for each section?
No, so it just has the form of a Canvas quiz. Like it's not like it's not doesn't have a due date or I'm not assigning it. It's not for
Are there questions for each section or quizzes, I mean?
I don't know if it's divided up that way. I think it's structured more like it's a test. So like it's just all thrown together and you have to figure out like what of the things we've talked about is the right tool here. Right, any questions on what's available, where it is? Okay, so we are going to go into 6.6 for a bit. We will probably finish this, if not by the end of class Wednesday. Then sometime Friday. I'm not going to move on after this. So after we finish 6.6, basically we'll just review for the test. And that'll basically be driven by you. So I've given you a lot of things you can look at to kind of start preparing. Start looking at it now because basically with whatever time we have after I finish this section, I'll just open it up to whatever questions you have and we'll work out whatever. That can be any of that stuff, old web work questions, old written homework questions, anything you want to talk about. Sound good? All right. So this section is called Improper Integration. Because we're going to deal with intervals or deal with integrals and intervals that might be infinite. Why aren't you please? So first thing I want to do here is this integral for a bunch of different values of that upper bound. So basically what I'm doing here is if we think about what this curve looks like, 1 over x squared, at least on the positive side of the y-axis. So if here's 1, basically what we're building up to is this. I want to find this area, but I don't want there to be a right end of this area. Even though this thing is infinitely long, I want to try to find an area that is just a number for that. So let's build up to that. So the first thing I want to do is to find this first area on just this unit interval from 1 to 2. So let's evaluate this integral. The integral from 1 to 2 of 1 over x squared. What is the integral of 1 over x squared? What's that?
Negative 1 over x.
Okay, negative 1 over x. And if I evaluate that from 1 to 2, I get negative 1/2 minus negative 1. So positive 1/2, right? So if I can get this area of this infinitely long region, it should be bigger than 1/2, right? All right, so now if I want to move out to 10, so the integral of 1 over x squared is not going to change, right?
No.
So still negative 1 over x. Now from 1 to 10, should get negative 1/10 plus 1 or 0.9. Do we have any sort of idea yet what the integral is going to be?
One.
So we think that, so if I go all the way out with to all the x values, essentially, we think we're building up to 1. So I will tell you that these next two are going to come out to be 0.99, yeah, 0.99 and then 0.999. So it seems like we are nearing 1. So how do we deal with it if we have to find an integral? I mean, writing things like this is kind of strange because infinity is not a number. So because of that, I'm going to express it this other way instead. I'm going to take this as a limit because even though infinity is not a number, I can think of these different t values as t gets really, really large of this integral. So I don't want to treat infinity like a number, but I can treat it as like I can treat it as like t is just getting arbitrarily large. So,
There it comes. Let's do-
question?
No.
Okay. So we know the antiderivative, which is -1/x. So now if I evaluate this integral at those limits, I get what? I get -1/t plus 1/1, right? Is this a limit that I can evaluate? So the 1's a constant. The limit is going to have no effect on the 1. But what's going to happen to -1/t as t gets really, really large? It's going to go towards 0, right? So that limit ends up being something we can evaluate, which is 0 plus 1. So even though this region that we're trying to find the area of has infinite length, its area is finite. Its area is exactly 1. Any questions about how we got there, specifically with how the limit gets involved with it? We happy? Yeah. All right. How about this one? I want to find the integral from 1 to infinity of 1/x. So should probably talk about a limit since we're trying to deal with ideas that are not numbers. So the limit is, you can use whatever symbol you want. I like to use t. The limit is t goes to infinity of 1 to t of 1/x dx. What is that antiderivative for 1/x? Natural log of
Absolute.
Yeah, there you go. So still want to carry the limit operator. The limit is t goes to infinity of natural log of the absolute value of x from 1 to t. So now where do I go from there?
We put T, and then we put ln, and the log of T. and that's-
Okay.
log.
So still want to deal with the limit. I'm going to drop the absolute value because we don't really care about negative values of t. All right. What's going on with this limit? Natural log of 1 is simply 0, right? So this is the limit as t approaches infinity of natural log of t. What is happening with that limit? what happens to natural log of t as t gets arbitrarily large?
All units large. on the side.
It also, so it gets larger and larger, right? Does it have a limit? No, it also grows without bound, right? So because of that, what can I say about this limit?
But it's infinity.
It's infinite as well. It's going to keep getting larger and larger. So does the limit exist? No. So that's one thing I remind people of is we said the limit is equal to something, it's equal to infinity. But that's really that's the specific way we're saying that the limit doesn't exist. It doesn't exist because the thing we're looking at just keeps growing larger and larger. So in this case, we say that this integral is divergent. So I did not mention it before, but the integral we looked at in the first case, it's convergent because it exists. This integral is divergent because it does not have a real value. What questions do you have? Okay. So now let's look at this thing in general. So we want to think about this. So with the first two examples we looked at would have been in this form, 1 over x to the power of p, where p is some constant. So what values of p do we think the integral will converge for? So I think we have one example or two examples so far, right? So if I make like a one-dimensional scale for p, we know that at 2 it converged, right? And at 1 it didn't. So it converges at 2. It does not converge at 1. Do we think it'll converge for values of a p that are bigger than 2? Go ahead.
What does converge mean in this?
So that, yeah, I tried to explain that, but maybe we could give her like an example of one that did converge. So I didn't mention the time because I wanted to show a divergent one first, but this one is convergent. Because when we took the integral, we got a real number. We got a value for that. So probably more useful to think about what the definition of convergence is for these integrals. If the integral yields a number, then it converged to that value. If the integral fails to do that, it diverges. So we've seen one example of each so far. So now that we're here, let's imagine this. Instead of this being 1 over x squared, what if it was 1 over x to the 4th? Do we think that would have converged? Yeah, I see some head nods. Why do we think it would have converged, those of you who are agreeing?
If it converge with 2, anything bigger should at some point converge, maybe not the same point, but it should.
Why do you say, why would bigger powers make it converge as well? You're on the right track, but
As the graph becomes closer to 0.
right. So basically, if we think about this graphically, the reason this converged is because the area was shrinking rapidly enough for it to converge, right? So we didn't graph it, but let's do it now. This graph over the same interval, you know, I probably could draw it identically. That's really good. But still, I mean, it goes to this point 1, 1. Still, it's going to have like this infinitely long tail. So the shapes, like in a lot of respects, are very similar, but this one diverged just because, you know, metaphorically speaking, there's the mass in that tail as x gets really, really big, it doesn't decrease at a rate, rapid enough to get that integral to converge, integral to converge. So yeah, your instincts were spot on that, if I converge at 2, it's going to converge for any value bigger than 2. So we have a good idea on those values of P. So if P is 2 or bigger, this thing's going to converge. What about if it's less than 1? What if it was like 1 over the square root of x, for example? So kind of by the same logic, looking at the opposite direction, anything less than 1 is going to converge. Because if that tail underneath 1 over x, so if this right here is 1 over x, if that integral diverges, then so are, like, for example, anything with a smaller power is going to decrease even less rapidly, so you're going to have even more area to consider there. So if the area underneath 1 over x got infinitely large, then anything bigger is also going to be infinitely large, right? But what about between 1 and 2? Don't really have a good idea what's going on between those things yet. So let's think about this. How about from 1 to infinity of 1 over x to the 3/2? Do we think that converges or diverges? Or does no one want to guess? We just need to do it. Okay, here's some converge, but like with an upward inflection, like you're asking me about it. Should we try it? Okay. So what is the antiderivative of 1 over x to the 3/2? Maybe you'd prefer to think of it like this. If I treat it as x to the negative 3/2, then what's the antiderivative?
-2 over root x.
How'd you get -2 over root x?
You add 1 and divide by 1, -1/2.
Right, so x to the negative 1/2 divided by negative 1/2. And then yes, if you simplify that, that becomes -2 over radical x. So if we look at this limit, after we plug in the limits, we get -2 over radical t minus -2 over radical 1. So 2 over radical 1 will just become 2. What happens to -2 over radical t as t goes to infinity? It goes to 0, right? So this area comes out to be 2. So now I know that it converges at 1.5. What about like 1.1? What's going to happen there, you think? At this point, I'll spoil it for you. Basically, anything bigger than 1 is going to give you convergence. Like so this integral diverges if p equals 1, and it converges for anything larger.
So for less than one is divergent,
Mhm.
and then greater than one converge.
Yeah, so let's we looked at a concrete example. We got a couple minutes left. Let's really try to make this formalized. What is the integral of x to the negative p dx? Knowing that p is a constant.
X with a negative p minus plus one over negative p plus one.
Right. So I mean, the way that we handle these kind of power rule integrals is no different. It's just now you're not looking at something as comforting as a number. You're looking at generic p. But yeah, still the logic is the same. I want to take that exponent, increase it by 1, and then wrong symbol here, divide it by my new exponent. And evaluate that from 1 to t. If I put a t in there, I should get t to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1, which is 1 over negative p plus 1. So if I start simplifying, I want to do this. I want to bring that t back down to the denominator so I can give it a positive exponent. So I bring down there, the whole thing becomes, I have to flip the signs on everything. So the exponent on t is p minus 1. And I'm going to let t go to infinity, right? The only way that t term is ever going to get smaller is if that exponent is positive. So since p minus 1 has to be positive, p itself has to be bigger than 1. Okay, should probably stop there. I got 1 until I want to start something new. Any questions before we go? Okay. I'll stick around for a bit if you have questions. Otherwise, I'll see you either in office hours tomorrow or Wednesday in class.